I wanted to do a couple of videos or a couple of problems for you for review for midterm number 2. And so this video is problems that, these ones are all taken from old exams, or from one particular old exam from 4 or 5 years ago. And so before we get started, I just want to mention, when it comes to using old exams, always be sure to, different faculty view using old exams differently. So some faculty operate, they give exams with a test bank where they sort of pull from old questions, and because they do that, they consider looking at old exams to be a form of cheating. Other faculty will use older exams, and they sort of say, once the cat's out of the bag, once the problem's out in the universe, they just kind of assume people will access it. And so for security reasons, they make new questions every single exam. They make new questions as soon as the problem gets out there. But different faculty have different views on that, and different faculty use old exams differently. So before you ask a colleague or an old upperclassman, hey, do you have some old exams from this class I could look at? Be sure to check with the faculty member to make sure, and check the syllabus. But be sure to get positive confirmation from the faculty member that they're okay with you looking at old exams, and that they don't consider that cheating, because there is a difference of, different faculty look at that differently. In this case, I'm going over old problems. So obviously these particular problems, going over them wouldn't be considered cheating. But another thing that can happen is some faculty sort of change their mind. So a faculty member could, reuse problems for a long time, and then they decide, this is too tough, so I'm just going to have a policy of don't look at old exams and don't use old material, that's cheating, and then I'm just going to switch to a test bank. So even if it was true for one point in time, it's not necessarily true for another. Best way to be sure is to ask. Always ask if it's considered cheating to look at old exams, to use old exams for review. So in this case, obviously I'm going through these problems, so it's not cheating for you to watch this video that I'm making for your benefit. But I just wanted to mention that right off the bat. So, okay, so a couple things to note. One, I'm going through these problems I didn't practice these. I haven't looked at these in 4 years. I'm just going through an exam that I wrote 4 years ago. The other thing to note is, when I did this exam, the class sessions that we had for this class were 110 minutes or 120 minutes per lecture. So this was a 7-problem exam for a 70-minute class. So the class was longer when this was offered. So this test was sized for having that extra time in class to do the exam. So just keep that in mind too. That the tests we have are sized to be for a 60-minute exam. Okay, so chapter 4, midterm 2 is all about chapter 4, and these review problems are all in chapter 4. And chapter 4 is really, the big concepts in chapter 4 are node voltage, mesh current, source transformations, Thevenin Norton equivalent, and superposition. Those are sort of the 5 things that we go about in chapter 4. So you can kind of expect those are sort of the 5 areas where you'll see questions out of on the exam. And we already had one question on node voltage in the last exam, but it is one of the major chapter 4 topics. So this first question is a node voltage question. And so if we analyze node voltage, we first set a reference. I'm going to pick this as 0, and I'm going to try to move through these kind of quick and not, these are topics we've gone over. I'm just kind of going over examples. It might be good use also to kind of, when we go to a new problem, pause it, try to do it on your own, and then get the feedback from me. Because the benefit of this is, anytime you watch somebody else do a problem, it's like, oh, it's easy. It's easy to watch somebody else do it. It seems to make sense while they do it. And then once you have to think about it on your own, sometimes it's a little more challenging. So maybe each new problem we get to, pause the video, try to do it on your own, and then see how I do the solution. And also keep in mind, like I said, I'm doing these, I'm working without a wire on these, so if I make a mistake, I'll make a mistake. I'll try to fix it or annotate it if there's a mistake, but I'm not going back. So okay, so then we label our remaining essential nodes. I'll just call these VA and VB. And then so we're going to have to write an equation for the current flowing out of each of these nodes. So current flowing out of VA and the current flowing out of VB. So at node VA, we have and at VB, we have okay. So these are our equations, and this is really half the battle. So getting these equations correctly is the big thing. This is the big chunk of what I want to see people being able to do when I'm grading an exam, when I'm giving it. You also need to be able to go from the equations to getting the actual correct numerical answer, but this is a big chunk of it. And that means if you make a mistake in this step, it costs you a lot of points. It costs you almost all the points on the problem if you make an error in applying the node voltage technique or mesh current technique. But from here, I'm just going to clean these equations up. So I'm going to multiply this one by a 6, multiply this one by a 2. So we're going to have 2 VA minus 18 plus VA plus and then I'll just clean this one up one more time. I got 2, 3, 6 VA. So 6 VA minus 3 VB equals 18. Cleaning up equation 2 now by multiplying by 2. We got VB minus VA plus VB plus 2 equals 0. So that's going to be 2 VB minus VA equals negative 2. And so we got this equation and this equation. We got to reduce them down to 1. I shouldn't have put a dash. It kind of makes it look like a negative. I'll probably just multiply this one by a 6 now and then add them together. So we got 12 VB minus 6 VA equals negative 12. And then, so adding this equation and adding this equation together, that gives us 9 VB equals 6. So VB equals 6/9. And plugging back in for VA then, so we'll just, I guess we'll just do it here. Yeah, let's use this one here. So VA equals 18 plus 3 times 6/9 divided by 6. That is 3 1/3. Okay. So VB was 6/9. VA was 3 1/3, and that's the answer I get. And that was part of it. And then it said find the power using passive sign convention of the current supply. So we know that VB, which was this is VB, and that was 6/9 volts. So then our current is shown, and our current, that 1 amp current is entering the positive terminal as labeled. So power for the 1 amp supply is going to be, because my 1 amp current is entering the labeled positive terminal of that 6/9 volts, power is going to be I times V. That's going to be 1 times 6/9. That's going to be 6/9 watts. 2/3, I guess. I don't know why I'm 6/9. 2/3. So all 6/9, the number formerly known as 2/3. So okay, so now one thing to note, right? That power for the current supply, so that current supply is dissipating. So it is extracting energy from the circuit. And that happens sometimes, and that's okay. Okay, problem 2. So one thing to note, a lot of students lose a lot of points because they don't read problems through. And I understand why that happens, because you're doing a test and you get to a problem, and when you flip to the problem, you say, oh my gosh, look at that thing. That is your mind immediately starts thinking, how am I going to analyze this? What am I going to do? How am I going to do that? And then when you do that, you don't ever go back and stop, and you immediately kind of freak out. You don't go back and stop and read it. So it's always worthwhile to spend the 15 seconds it takes to read through the problem carefully. That always pays off. That always pays off, because a lot of times students will do way more work than they have to because they didn't fully read what they had to read. So in this case, the problem is saying you do not need to solve for the current. So basically it's wanting you to write the mesh equations, and the meshes are labeled 1, 2, 3, 4, etc. And it just wants you to write the equations. It's not asking you to solve the equations, but it is asking you to say it shouldn't contain any other variables other than the mesh current. So there's dependent supply here. So basically it's saying don't leave that lambda in there. Actually write it in terms of these unknown variables. So let's analyze this the same way we would any other mesh current. So we got our meshes here. A couple things to note when we draw these meshes is, well, mesh 4 here is just 5 amps. So immediately we know that I4 equals 5 amps. And so technically it says you have to write a sequence of a series of equations. So technically you could write one equation as I4 equals 5 and then just put I4s everywhere in your equations, or I'll probably just combine. I'll probably just knowing that I4 is 5, just not use I4 anymore. I'll just use 5 every time there should be an I4 from here on out. So the other thing is we have a current supply in between two meshes. So what is that? That is the case where we have to use a super mesh. And it's a dependent current supply, but it's a current supply. So current supply in between two meshes is super mesh. The fact that it's a dependent current supply means after we get this equation done, we're going to have to plug in a substitute. We're going to have to plug in a little equation for that lambda, but I don't care. It's a current supply. We're just going to treat it like a current supply for now. So it does mean, though, that we're going to have to write a super mesh equation for this one, though. All the way around here. So let's go ahead and do that. So we have 20I1 plus 5 times I3 minus I4, which is 5 amps, plus the 2 and the 15 can be combined. I mean, we can combine them into 17 ohms, and that's fine. So I'll probably just do that right now. I could have done 2 and then the 15, but the math is going to immediately work out the same to be 17. So 17 times I3 minus I2, and then and that's it, equals 0. Now we can't forget that we did a super mesh, so we're going to have to come back and write this equation relating these two currents together, but we'll do that later. So, and then we'll do around mesh 2. So this was around the super mesh. Now around mesh 2, we have negative 16 plus 3I2 plus 17 I2 minus I3 equals 0. Okay, And then we have that last equation, which relates these two currents together. So we have to say I1 minus I3 equals, I can't see it now, 3 lambda. So right now, these are my 3 equations for my 3 unknowns. Remember, this fourth one is not an unknown. So my only unknowns are I1, I2, and I3. I have an issue right now, though, because I still have a lambda in here, so I have to get rid of that lambda. So the question is, what is lambda? Lambda is the voltage across this resistor. We actually already wrote that voltage. We wrote that here. So all we have to do is basically replace this lambda with okay, so now I have these 3 equations. This does say ensure the equations are simplified. So we should go back here and simplify these equations. And that's fine. So simplifying the super mesh equation, we have 20I1. Then we have, looks like negative 17I2. And then we have 5 plus 17I3. So that's going to be, and then that all equals, we have a 5 times a negative 5, but flopping that to the other side of the equation, we get, sorry, it's not 25 amps. It was 25 volts. If we're going to write units, we might as well write the correct units. Okay, and then this equation, simplifying it, we have, how many I1s do we have? We have 0 I1s. We have 3 and 17I2, so it's 20I2 minus 17I3 equals 16. Okay. And then for this equation, we have, this one's a little weird because it's kind of stuff on both sides of the equation, so I might kind of clean this up a little bit more here. So we have 15I3 on this side, so let's move that over to the other side. So we have I1 minus 1I3 minus 15I3, so minus 16I3 equals negative, it's a negative 5 times 15. So that's going to be 75. Hopefully I did that right. Yeah. Okay. So, yeah. I1 minus 16I3 equals negative 75. Okay. And that wasn't the end of the world. We could have had you solve this. This could have been solved. If you were solving this, though, you probably would have solved it in matrix form. If we'd been asking for the solution, matrix form probably would have been appropriate, which would have been okay, because it would have just, if you had done this in matrix form, it would have been 20, negative 17, 22, 0, 20, negative 17, 1, 0, negative 16. Right, so it wouldn't have been the end of the world, whatever method, if you want to invert and multiply, if you want to use an augmented matrix, whatever, if you had been asked in this, I'm kind of going an extra step. You weren't asked to do this, but if you had been asked to solve this, you would have wanted to use probably a matrix, and you would have just done it using your favorite technique. Here's the issue with using a matrix. It's fine on the test to use a matrix. It's fine to use your calculator to solve the matrix. However, when you're solving a set of equations using a calculator to solve the matrix, if you're unable to get the right, if you have the right matrix, but you're unable to get the right solution, generally we're not very forgiving in grading that, because you need to be able to use the tools you're using when you're solving these problems. So I've had a lot of students where they'll do a test, and every problem they do a matrix solution, and they get them all wrong. And they tell me, oh, I was trying to use an augmented matrix, but my calculator does it weird or something. And generally what that tells me is you weren't using the calculator to do your homeworks. You weren't, you clearly weren't able to use the calculator to get the correct answer using this matrix form. And that's a big part of engineering, is being able to use the tools of the trade, including calculators, to do matrix manipulation and things. So be sure, as always, know how to use your calculator, have backup batteries for your calculator, whatever you need. Make sure you can get the right answer with your calculator, because if the work you're doing is done by a calculator and you just leave a note when you're doing your exam of plugged it into the calculator, this was the answer, if you didn't get the right thing on the other end, we have to kind of assume the worst. We have to assume, you're not able to use a calculator to solve a matrix, and that's kind of a big deal. So the benefit of doing it by hand is, if I can see your math and there is a mistake, it's easy for, I can sometimes see, oh, you kind of wrote this 2 like a 3, and so this 2 became a 3 at this point. And then I know it wasn't a fundamental issue with your ability to do math, it was just sloppiness, which still you're going to lose points. But whereas if you can't use a matrix, if you can't use a calculator to solve a matrix, that's a fairly big fundamental misunderstanding or fundamental inability to use the tools of engineering. So just wanted to give that heads up. If you are using a calculator, whatever method, inverting matrix, augmented matrix, whatever, be sure you know how to use your calculator. Be sure you have batteries for your calculator, etc. Be prepared for that. And again, it should be what you've been doing on the homework all along. Okay, I remember this problem. I remember giving this problem, and I remember two people got this problem right when I gave this test. Because I think it was it was like a dependent on a dependent or something like that. Yeah, which is okay. Sometimes you get tough problems. It's good to know the process. So I'm warning you, if you want to pause the video and try it yourself, take a crack at it. But I definitely remember this problem. Okay. All right, so this problem, and I guess I warned people in it, it's a beast. I recommend you do it last. It's not even remotely clean. Okay, you don't always get that warning. Some problems come out clean, some problems don't come out clean. You can't assume one way or the other. You can't assume. Anyway, the only thing you can do is, if you get an answer and you're not sure if it's right, put a star next to it. If you don't feel so great about it, put a star next to it, come back to it. If you get the rest of the problems done right, if you get the rest of the problems done on the test, and look back and say, actually, I don't know if you can look back in Canvas. I think you can. But go back and at least when you're doing it on paper or something, go back and double check your work. But, actually do the mesh current or node voltage around the loops. And there's plenty of ways you can sort of check your work and make sure you're on the right path. Okay, so node voltage technique. I label the nodes, and I mostly label the nodes here so it makes it easier to grade these if everybody's using the same nodes with the same labeling conventions. But okay, so we're just going to, so this one is obviously going to have to be our reference because it's the only unlabeled essential node. And we're going to have to write equations at VA. And we're going to have to write equations at VB. And at VC. Okay. So at VA, so immediately we kind of have a tricky one. We got a voltage supply and a resistor. Well, my question is always, anytime there's a resistor, my question is, what's the voltage across the resistor? If I want the current flow in this direction, and I want to use the equation V equals IR, I have to find the potential across the resistor oriented like this. So what's the voltage on this side? Well, it's VA, but then we went down 10 volts. So it's going to be VA minus 10 volts. And that's the voltage here is VA minus 10 volts. And the voltage on this side is just 0. So minus 0 divided by 3. So that's that current flowing flowing down. And then in the up top, this current is 4IS. We're just going to leave it as 4IS for now. And then going to the right, this current is, now one thing is we have IS labeled here. And a lot of times, you know, that's a label that's being used by another dependent supply. But a lot of times students would see that and they'd say, oh, okay, like, let's just put a negative IS. And, you know, they'll just say, hey, just put a negative IS. We're going to have to substitute for IS anyway. You're eventually going to have to write this out. You could put a negative IS, but usually it's best to, if you can write it without the dependent supply or without too many dependent supplies, it's generally better to do that. So we can do it either way. But eventually we're going to have to substitute for these. So this one's a little weird because the voltage is dependent on VP and this current is IS. So you're going to get dependent no matter what. But eventually we're going to have to come back in and substitute for all these variables. So let's just write it as the voltage here minus the voltage here divided by 1 ohm. So that's going to be VA minus, so it's VB plus 3 VP. Divided by 1. And so it should be noted, this is the equation for the current flowing this way. So IS is actually going to be the negative of that. IS is going to be the negative of that equation, which I'm sure we'll see that later on. And then was that all my currents in that one? Yeah, that equals 0. Okay. So VB, at VB we got negative 4IS plus, now we got the current going the other way. And again, we could write it as IS, or we could just write it as VB plus 3VP divided by minus VA divided by 1. And again, this equation is the negative of this. Okay, this is the negative of the other one. So this equation here now, this equation here is IS. So something to keep in mind, that is IS. And before I'm going to forget something if I keep yammering here. VB minus, it looks like a 5. VB minus VC over 4. And, oh, that's it. And then lastly for VC, we have VC minus VB divided by 4 plus VC over 10 plus negative 2. VC was the only one that was normal. This is a tough problem. So, you know, on tests usually there's a mix of, you know, a couple of easy ones that most people should be able to get, a couple of normal ones that, you know, kind of moderate difficulty, and then a couple of challenging ones, a couple of ones that really kind of push your ability to do things, to work these problems. Okay, so now I've got 3 equations, but I still have to come back in and substitute for these things. I still have to come in and substitute. So this one, so yeah. So one thing to note, right? This was IS, right? That is IS. So IS equals VB plus 3 VP minus VA divided by 1. And now let's also put in this VP here. So what's VP? Now, VP is VB minus VC. And a lot of people instinctively say, oh, VP is VB minus VC divided by 4. No, that's the current. That would be the current flowing that way. VP is just the voltage, which is VB minus VC. So this one is VB plus 3 times VB minus VC minus VA. That's 4 VB minus 3 VC minus VA. So this is IS. And actually now, looking at it, I kind of do want these, because of all this manipulation that we just did, we're gonna have to redo here and here. I'm actually gonna I'm gonna go back on what I said and I'm gonna rewrite these in terms of IS. So this one was 4IS. This one was negative IS. So that cleans up to 3 IS total. And this one was negative 4 IS plus IS. This one cleans up to negative 3 IS. And then we have to substitute this in for both of these. And I don't want to do any more of this one. So this one bored me. I don't have enough space to do any more of this. But you see, though, once you substitute in this equation, all three of your equations now are just in terms of VA, VB, and VC. So now it just becomes a matter of getting these into combining the equation, simplifying it. I ran out of space. I know there's no way I have enough space to do this one. Again, though, this is a challenging one. I remember doing this one, and I remember there was only like 2 students who got it right. So, but even when you don't get it right, being able to identify these things is really valuable on a test. So when I'm grading this test, when there are these problems where the problem is designed to push to test the limits of how well people can do these, then when I'm grading and giving partial credit, my question is, how many of these things did you identify? Did you identify that VP was VB minus VC? Did you identify that IS was, VB plus 3 VP divided, minus VA over 1, right? So really the partial credit that I give is based on how far through this process were you able to do this successfully. And then, if you weren't able to juggle all the equations, and who knows, I might have misjuggled an equation right now already. If you weren't able to juggle the equations correctly, the bigger question for me when giving partial credit is, which of these tricks were you able to identify and understand and realize what they were and how to solve them? All right, this one looks a little better, a little more normal. Find the Norton equivalent of the circuit with respect to the 2 terminals in the circuit below. Okay, so Norton equivalent, Thevenin Norton equivalent for me, if I'm analyzing it, I always immediately try to do the resistor trick. So I always try to find the REQ. So if I'm I'm going to try to find REQ. So open circuit the current supply, short circuit the voltage supply. That's a 4 and a 5 and a 20. So then we have 4 plus 5 in parallel with 20. That should be 8. 5 in parallel with 20 should be 4, but double check. Yep. So that's 8. So boom, we got REQ. That's good. So now the question is just, do we want to do short circuit current, open circuit voltage? This one, open circuit voltage is going to be weird because if we do open circuit voltage, we're going to have to find the voltage across this and the voltage across this, and that's going to be it's a simpler equation, it's a simpler circuit, but I'm tempted to find short circuit current here. Maybe I'm making a mistake, but let's find short circuit current. So put that wire there, find the short circuit current. Let's do a mesh current here. So the good thing is, we'll call this 1, 2, 3. The good thing is we know 2 is 8 already. All right, now let's see how this math goes. Maybe I made a mistake. We'll see. Negative 120 plus 5 times I1 minus 8 plus 20 times I1 minus I2 equals 0. And then around equation 3, we have 20 I3 minus I1 plus, I do this, why do I do this? 4, goodness, times I3 minus 8 equals 0. All right, hold on to your seats now. And this is where we see whether or not I make a math error as I go through this. And when I do make a math error, everybody gets that cathartic, ha! He did it too, and he has a PhD. But one thing you don't get is I already passed this class, so I'm done. I am done. I've paid my debt. All right, so we got, for the first equation, we got 25 I1 minus 20 I2 equals 120 plus 40, that's 160. Okay, and for the second equation, we got negative 20 I1 plus 24 I3 equals 8 times 4, 32. Okay, is there a good way to clean this up? What did I get an I2 there? All righty, good way to clean this up. Not really. Multiply this equation by 4, multiply this equation by 5. How about that? How about that? So we got 100 I1 minus 80 I3 equals, now whenever people multiply through by the number, they always forget to, one of the biggest areas they make a mistake is they forget to do that constant on the other side. They forget to multiply that thing through too. So this should be 640. Okay. And then the second equation, negative 100 I1 plus 96 I3 equals 5 times 32 is going to be 150 plus a 10. See how I did that? When I learned math in school, I don't know how old everybody is. I don't know if people do the new math, but I was prepared to be as outraged about like the new way of doing math as everybody else. It's just because math is math, right? Math is math. But it turned out the new math, the way they teach it, is the way that I always did it in my head, which was not the way I was taught anyway. So I kind of feel like the way they teach math is sort of, it's come to me. So I can't be that upset about it. So maybe I was doing something right all along. All right, stop talking, John. You're not gonna be able to get this done. Okay, so we got 16 I3 equals, oh boy. I've got to get a calculator. That's 800. This is feeling good. This is feeling good, folks. This feels good. 16. So we got I3 equals 800 divided by 16, which should be 50. Feels good. Feels right. I don't know. If that's not right, I got a very clean mistake if that's not right. All right, so I3 was the short circuit current. So going back to it, I3, this current I3 is the current through that short. So that is the short circuit current. So then our Norton equivalent here should be 50 amps in parallel with 8 ohms. Okay. And I got my Norton equivalent, and then my eyeballs immediately go back to the problem and say, was I doing everything it asked for? Was it asking for an, because sometimes there's that extra thing, and man, it hurts when like there's a good student and they know their stuff and they do it right, and then they just don't answer part B, and they completely ignore it because even when you read it through, don't get too excited that you get a nice clean number. Oh, it's a 15 and 8. It's got to be right because it's super clean. And then you get excited, and then you don't look back and say, oh, there was a part B that said, what's the power dissipated by the whatever, or something like that. So be sure to check for part Bs. Always be sure to check for those pesky part Bs. Okay. All right, this is new for me. It's been 4 years since I've seen these things. Some of them, the notorious ones I remember, but the rest of them I don't remember this one. So what resistor value should be connected between the terminals below to result in maximum power transfer to the resistor? So the first thing here should be, what does it mean to have maximum power transfer? The maximum power transfer, which we talked about, was the load resistor you connect to a circuit to achieve maximum power transfer is a resistor equivalent to the Thevenin equivalent resistance, which is the same as the Norton equivalent resistance. So how do we find the Thevenin equivalent resistance or Norton equivalent resistance? 2 ways. We can find the short circuit current and the open circuit voltage and take the voltage divided by the current, or we can use the shortcut. So in a problem like this, so we can set all the supplies to 0 and find the equivalent resistance relative to the terminals. In this case, because all we care about is that resistance, that's really what we're being asked to solve for. I really hope that technique works out okay here. So I'm going to try to use that technique here. So open circuiting the current supply, short circuiting the voltage supply, I'm going to get 6 here, and a 3, and a 9. Okay, and so I get a 6, and so combining these is 12, so now this is, it's really important to be careful about the terminals here. Right? So if you're doing something with respect to the terminals, those count as a connection. So a mistake students might make here is they might combine this 12 and the 6 in series. These are not in series. They are not in series because even though they share a node, there is something else. That terminal connected to that node counts as something connected there. So it doesn't, you can't just say the 12 and the 6 are in series. You can say, because they do share 2 nodes, that they're in parallel. So 6 in parallel with 12. It should be 4, but I don't trust myself. What did I do? Done. So that's, again, recognizing that all it's asking for is for us to find the Thevenin equivalent resistance. Big time saver, and that happens a lot in these exams. Is students think they have to solve for more than they do, and then they end up taking too long, and then they end up getting burned for time. So don't mind me. I'm just sponsored by Rockstar Recovery, so smash that like button, folks. It's way too. I'm way too tired. I'm way too tired right now. I'm gonna get in trouble. All right, problem 6. Problem 6 looks like it made it in trouble with this thing. But what does it say? Find the voltage across the 140 ohm resistor by making a succession of appropriate source transformations. Ooh, okay, this is a source transformation one. So maybe not so bad. So 1, it's saying find the voltage across the 140. So if it says find the voltage across the 140, we are not touching that sucker. I mean, looking at this thing, it's tempting to combine that 10 and the 140. They're in series. But the problem asks us to find the voltage across the 140. So that sucker is sacred. We are not touching that thing. So leaving that thing alone, we're going to combine everything else. So what can we do? Looking at the rest of the circuit, do we have anything in series or in parallel that we can simplify? I do not see anything. I do not see anything. So if you see something in series or parallel, maybe I'm missing it, or maybe you're seeing something you shouldn't be seeing. So, but I do see that if I do a source transformation here, then I'll have some stuff in parallel. So we got 150 volts divided by 300 ohms. That's 500 milliamps. So I can replace this with a 500 milliamp in parallel with the 300. And then there was another 500. And that was in parallel with a 60. And then we had the rest of the circuit over here. So I'm going to, this is okay. When I say redraw the circuit, I'm not going to do that because I don't have enough space on this slide. But when I say redraw the circuit, basically what I'm trying to get at is I don't want you to make too many transformations to the point where I can't follow your work. So so every time you get to the point where you are converting and then reducing, be sure it's clear what changes you're making. I don't want you to have to draw an entire circuit 50 times. I just want you to be clear at every major intermediate step to show me, okay, what was your intermediate circuit? That way, if you mess it up, I can see where the mistake happened. That's what I mean when I say redraw. So here, now this is something I really want to talk about in this video because I didn't focus on it in the original video, and it's really crucial. When you have current supplies in parallel, you can combine the currents together. You add them if they're in the same orientation, or if they're in two different orientations, you have to sort of take one direction minus the other and then show the equivalent current flowing in that direction. And the same is true with voltage supplies in series. When you have voltage supplies in series, you can add them together. So basically, we have this, all four of these things are in parallel. The 60, the 300, the 500, the 500, these are all in parallel. We have 500 milliamps flowing up. We have 500 milliamps flowing up. We got two shotgun 500 milliamps flowing up. That's the same as 1 amp flowing up. So we have a total of 1 amp flowing from this node to this node. So we can actually add these together and replace these with a 1 amp current supply. And then we can also take the 300 and the 60, and we can say 300 in parallel with 60 should be 50, but it is 50. Okay, so we just combined that. So now this portion of our circuit here is now reduced to this over here. Okay. Alrighty, so now this is probably a good time for us to take a bite at another part of the circuit. So what about up here? We can combine, if we convert this to a current supply in parallel with a resistor, then we'll have two current supplies in parallel. We'll be able to combine those together. So let's do that. So we got 120 divided by 80. That's going to be 1.5 amps. And we got to be very careful with directionality here. We have to be very careful. So I'm going to basically redraw the entire circuit right now. So I have so now this 1.5 amp current supply in parallel with an 80 ohm resistor. I didn't leave myself a lot of space here. And then there was this. Now we got to be careful with direction. The arrow points towards the positive side of the voltage supply. So the arrow always, yeah. So it's going to be like that, and this one here was 1.5. Okay. And then let's not forget about this 50 down here, and then let's not forget about this 90 here. Then here's our sacred 140 over here. Okay. All right, so now we have 1.5 amps flowing to the left and 2 amps flowing to the right. So that is equivalent to 0.5 amps flowing to the right. And when I say the right, I mean basically from this node to this node. So 1.5 to the left, 2 to the right, that's the same as 0.5 to the right. So we are going to take this out and replace this with a 0.5 amps. Okay. All righty. So now what can we do? So now I would basically, you know, every time you look at it and you say, well, there's nothing I can combine. Don't just get desperate and start combining things, right? A lot of people start doing stuff like they say, oh, I'm going to combine the 50s. Can't do that. They're not in series. Oh, I'm going to combine the 80 and the 10. Can't do that. Not in series. Oh, I'm going to combine the 50 and the 80. Can't do that. They're not in parallel. Oh, I'm going to combine the 50 and the 90. Can't do that. They're not in parallel, right? So really make sure you don't combine things you can't combine. And if you can't combine anything, that's usually when you want to say, I need to do some source transformation. So looking at the circuit, we have a 50, and then we have this mess, and then we have this mess. If we convert this into a voltage supply in series with a resistor, and this into a voltage supply in series with a resistor, we are going to have a whole string of things in series. And one thing you know about things in series, you can swap the order of them and combine them. So let's convert these into a whole bunch of things in series. So just doing a little math here, we got 50 times 1 equals 50 volts. And then we have 80 times 0.5 equals 40 volts. So we can redraw this thing now. 50, and then we have a voltage supply in series with the resistor. So the current was pointing up, so it's going to be positive oriented on the top there. And that one was a 50 volt supply, and the resistor is still a 50 ohm resistor. And then this on this other guy over here, we had a now again the current supply is pointing from this. It's going from this node to this node, so the positive side has to be oriented on this node. And that one was 40, and then in series with an 80. And then we had a 90 and a 10. So now all this stuff in series, we can shift this around. So we have a 50 and a 50 and an 80. We can combine those into 180. That was easy. All right. And then we have a 40 and a 50 here. So the 40 and the 50, the way they're oriented, these can be combined into a 90. So again, voltage supplies in series, we can add them if they're in the same orientation. If they're in opposite orientations, we have to do kind of a, well, it's going up 50 and then down 40, so it's up 10 or something like that, right? So we have to recognize what the net voltage increase is, you know, depending on the orientation, and then we can just replace it. So now these can be combined into a 90. And then I might have to do a little erasing here because I'm running out of space. Yeah, let's do a little erasing here. Okay. So now we have, again, there's nothing we can reduce. There's no resistors in series or parallel. So once again, on this one, I'm going to do a source transformation here. So 90 divided by 180 is 0.5 amps. So I'm going to redraw this as 500 milliamps. In parallel with 180. And then that's in parallel with a 90. And then we have the 10 here, and then let's not forget about our untouchable 140 over here. Now we have an 80 in parallel with a 90. Sorry, a 180 in parallel with a 90. So $60. So we can replace these with a 60. Okay, now when you start to get close to the end here and everything's clean, don't get too excited. Right? Everybody always, everybody gets too excited when it gets right near the end. They get just, yeah, they always make a mistake. They say, oh, 60 plus 10 is 70 or something. No, you can't do that yet. So we still gotta keep working on this. So if I convert this into a voltage supply in series with a resistor, it's going to be in series with that 10. So I can do 0.5 times 60 equals 30. So I can redraw this as a 30 volt in series with a 60, in series with a 10, and then there's my 140. Okay, and I can find the voltage across the 140 now. So I can find the voltage across the 140. I could combine these into a 70 if I want. I didn't have to though. And now it's just a voltage divider problem. So now it's just voltage across the 140 is going to equal 30 times 140 divided by 140 plus 70, 20 volts. Okay. Hope I did it right. It sure felt good. If I made a mistake, I'm sure you'll be happy to point it out. But so that was a good example, because that example went through, that was a big one, first of all, big problem, but it went through combining current supplies in parallel and voltage supplies in series. So hopefully it kind of made sense as I was doing that. But really with these, you want to be careful, do the problem on your own and check, the biggest mistake people make is when they're replacing a voltage supply in series with a resistor with a current supply in parallel with a resistor, they don't put it in the right spot. They don't put it in. You can always isolate the two terminals it's touching, right? This current supply and the resistor are here and here. Those should be the two nodes that when you replace it, those are the two nodes where your voltage supply in series with the resistor inserts. So a lot of times the mistake people make is when they replace it, they don't replace it in the right orientation, the right direction, and it messes stuff up. So try it on your own. Check your work versus my work. Let's hope my work was right from the beginning. Okay. Use superposition to find the voltage across 25 ohm resistor. So superposition, one of the biggest, and I can't remember if I talked about this on the video. It was a week ago, which in 2020 days, that was like a month ago. So superposition is mostly useful for when we're able to simplify a circuit to the point where we don't have to use node voltage or mesh current. So I tend to like superposition problems where when you use superposition, it's just a voltage divider, current divider to find the unknown values. That doesn't mean it's going to be that way on the exam, but that's where I find value in it. There's another reason for that. And the other reason for that is there's an exam you take. If you ever want to be a professional engineer, and some of you will become professional engineers, some of you won't. Be careful, they'll tax you if you're, in some states, they'll tax you if you're a professional engineer. I am not a professional engineer. It's less common when people have a PhD to be a professional engineer. Being a professional engineer means you're able to stamp your work, to put your professional engineering stamp on your work, which is sort of a way that you certify your work. It also opens you up to liability. But if you do power engineering, there's a lot of areas of engineering where it's going to be expected that you have a stamp that you be a professional engineer. There's other areas of engineering where it's going to be more rare for you to be a professional engineer. We'll talk about it later, but my point is, there is an exam you take to be a professional engineer, and there's a couple stages to it. The first stage of the exam is you take what's called the Fundamentals of Engineering exam, which is basically an exam to make sure that you got an education that reasonably taught you how to do electrical engineering. And that's an exam that you take right after college. And then after you pass that exam, you work for a few years underneath a professional engineer, and then you take a follow-up exam that's more based on your profession's expectations. But the exam you take as a the FE exam, which you take right out of college, you take it your senior year. That exam is has a lot of questions that sort of ride this line of, if you know the trick, they're quick to answer. If you don't know the trick, it's going to take you more time. And so they have a lot of questions that are about this size. They're about this size of problem where you can really do it with any technique you want, but sometimes if you do it with like superposition, it'll be a little bit faster maybe. But this is the size problems I always kind of like with superposition. So use superposition to find the voltage across 24 ohm resistor as shown here. So you know, two circuits. I'm going to draw the circuits right now. So if we have the 12 volt supply and set the 6 amp supply to 0, then our circuit is going to be like this. And then current supply, and then set the voltage supply to 0 and leave the current supply in there. And we're left with okay. So this is fairly straightforward. So this is finding this voltage in either case here. So first of all, finding this, and then we'll call this V2. So V1, so solving it the first time with the one supply in there, this is just a voltage divider. It's going to be 12 times 24 divided by 24 plus 12. And this is going to be 8. Okay. And then this one, so this one's a little weirder, but basically the 24 and the 12 and the 6 are all in parallel. So if we want to, we could redraw this like this. So if you tell yourself, wait, how did he redraw that like that? You can't just redraw it. Well, all I did was I switched the order of things in parallel, which is okay. So think about it. Like if you had a floating circuit like this, and you grab the 24 ohm resistor and the 6 amp current supply, and you just twisted their wires, well, then you have this drawing, this representation. I prefer this representation over here. And it also helps me see that if I'm trying to find the voltage across this 24, that's the voltage across both of these, right? This voltage across the 24 is also the voltage across the 12. So the 12 and the 24 in parallel, I need to know the voltage across both of them. So let's just combine them in parallel. So 12 in parallel with 24. Eight. So if I have 6 amps, 6 amps, and 8 ohms, the voltage across that is going to be 48, right? Okay, now we can't forget, right, that was V2. So V1 was 8, V2 was 48, so V total equals V1 plus V2, that equals 56. All right. What if we wanted to check our work? What if we didn't trust ourselves that it was 56? If we don't trust ourselves that it's 56, we can just do like Kirchhoff's current law or something. I just do a quick Kirchhoff's current law. So I'd say this current plus this current plus this current has to equal 0. So 56 divided by 24 plus negative 6 plus 56 minus 12 divided by 12. So that should all equal 0. So 56 divided by 24 is 2.3, repeating. And then 56 minus 12 divided by 12 is going to be uh-oh. I don't like this. Something feels wrong. Definitely made a mistake somewhere. No, that's why we check it. That's why we check it. Where could there have been an error here? Where could there possibly have been an error? Oh, 44. Hello. Jeez. There's not an error. Ah, it's 44 divided by 12, not 48. So yeah, so we get plus 6 plus, yeah. Perfect. All right, minor freak out. But, yep, checked our work. If we had time, I don't think we had time. Anyway. All right, that's a couple of review problems. If you wanted something extra to look at, if you wanted to see some problems that might be a little fresh, there it is for you. Consider the review for midterm 2 officially done. So thanks for watching.